menjelaskan obat tentang analgetika, Antiparkinson, dan juga sedatif-hipnotik.
Assalamualaikum warahmatullahi wabarakatuh. Dengan saya Ibu Novi, kita akan belajar tentang medication, yaitu obat-obat yang digunakan untuk menurunkan nyeri. Kita belajar tentang neuroanatomi nyeri ya. Ketika ada stimulus nyeri, akan dihantarkan oleh neuron namanya nociceptif. Ini neuron yang khusus untuk mengantarkan nyeri melalui spinal cord menuju ke otak. Nociceptif ini membawa sinyal menuju ke korteks cerebral, itu pusat dari nyeri. Ke korteks cerebral ada, ke talamus juga ada. Nah, dilihat dari mulai bawah, ada stimulasi nyeri pada reseptornya, namanya reseptor nociceptif. Kemudian menuju ke dorsal root, masuk ke spinal cord ke atas, ya, dihantarkan oleh neuron ascending, neuron yang ke atas, ke daerah namanya talamus. Kemudian dari talamus diantarkan ke korteks cerebri melalui neuron talamikortikal. Setelah sampai korteks cerebri tadi, nyeri terus bisa dipersepsikan ya. Apakah saya nyeri seperti apa? Nah, ada tadi kita belajar tentang neuron yang meningkat ya, tadi yang ke atas ascending. Ada yang kebalikannya, yaitu descending neuron. Ini fungsinya untuk menghambat transmisi nyeri. Kalau yang ke atas dia menginformasikan ada nyeri, kalau descending neuron itu menghambat nyeri. Nah, ada obat namanya opiat like peptide. Opiat like peptide itu seperti apa? Dia akan memblok sinyal nyeri di spinal cord, sehingga nyerinya tidak akan terpersepsikan di korteks cerebri. Ini fisiologi nyeri dipahami ada 4 fase: transduksi, transmisi, kemudian persepsi dan modulasi. Transduksi adalah proses diterimanya contoh prostaglandin, histamin, sitokin, kemokin pada reseptor, nociceptor namanya. Jadi dari prostaglandin itu ditangkap oleh nociceptor, itu disebut sebagai transduksi. Setelahnya aktivasi dari nociceptif ya akan menuju ke dorsal horn. Nah, ditransmisi oleh 2 serat, yaitu serat delta A dan serat C. Itu namanya adalah proses transmisi, penghantaran, namanya proses transmisi. Serat C dia kecil, tipis, sehingga menghantarkan nyeri dengan cepat. Berbeda dengan kebaliknya, dengan lambat. Sedangkan delta A dia fast transmission, serabutnya lebih besar, tetapi sehingga menyebabkan dia lebih cepat. Sampai ke dorsal horn, kemudian diantarkan ke atas oleh ascending neuron, dibawa ke talamus sampai ke korteks. Sampai di talamus atau korteks akan ada persepsi nyeri. Oh, kita merasa nyeri ya. Oh, barusan teriris pisau, ternyata nyeri tangan saya. Nah, itu sudah sampai ke tahap persepsi. Hitungannya cepat, bukan? Dari proses transduksi, transmisi sampai ke persepsi. Proses selanjutnya ada proses modulasi oleh descending neuron ya. Neuron ini akan menghasilkan endogenous opiat. Contohnya adalah serotonin, norepinefrin, apalagi dopamin, beta endorfin. Nah, itu yang akan menghambat proses penyampaian nyeri oleh ascending neuron memblok. Jadi descending neuron akan menghasilkan tadi endogenous opiat untuk memblok nyeri sebelum dihantarkan ke talamus dan korteks cerebri. Paham ya? Ada 4 fase fisiologi nyeri: transmisi, persepsi, dan modulasi. Oke, kita lanjut. Ini adalah impuls neuron yang mentransmisikan, ada sinap, menerima. Sinap adalah hubungan pertemuan 2 neuron, satu di dendrit, satu akson. Ini yang bagian atas seperti ujung tulang itu adalah akson, bagian yang bawah adalah dendrit ya. Jadi ada sinap pertemuan. Akson akan mengeluarkan neurotransmitternya. Neurotransmitter keluar kalau ada kalsium. Setelah neurotransmitternya keluar, akan ditangkap oleh reseptor pada neuron yang berikutnya. Kalau neuron yang berikutnya tidak ada reseptor atau reseptornya terhalangi obat misal, maka neurotransmitter tersebut tidak akan menempel pada neuron yang kedua. Proses apapun itu, bisa nyeri ya, akan terhambat. Ini impuls nyeri ya. Ada substansi P. Kalau di buku fisiologi disebut substansi P. Saya lebih suka menyebutnya sebagai prostaglandin. Di buku biokimia disebut prostaglandin. Ada primary akhir dengan second order. Prostaglandin dilepaskan karena adanya influx masuknya kalsium ke akson. Prostaglandin keluar, ditangkap reseptor. Pada sisi kiri itu yang ada merah-merahnya itu adalah reseptor. Akhirnya efek prostaglandin apa? Memvasodilatasi, meningkatkan vascular permeability, stimulus nociceptor neuron, menstimulus saraf yang menghantarkan nyeri reseptornya. Ada lagi sel mast ini berperan dalam inflamasi. Dia akan mengeluarkan mediator ya, efek dari degranulasi, pembongkaran granular-granular ya. Jadi sel mast itu mempunyai granularnya banyak. Kemudian ini akan dilepaskan saat ada inflamasi. Proses degranulasi ini akan mengeluarkan histamin ya, mengaktifasi neutrofil. Produk sintesis prostaglandin, ada tromboksan, ada leukotriens. Ini tentang bagaimana sintesis prostaglandin dan tromboksan. Tadi substratnya adalah fosfolipid, dia akan menjadi asam arachidonat. Kemudian oleh enzim siklooksigenase bisa menjadi siklik endoperoksida. Terbentuklah prostaglandin dan tromboksan. Nah, enzim COX ini ada subkelasnya, subkelas 1 pada kondisi homeostasis dan subkelas 2 pada kondisi inflamatori. Oke, berikutnya kita bagaimana pembengkakan bisa menyebabkan nyeri. Pembengkakan akan mengaktifkan nociceptor neuron ya, karena ada penekanan sehingga timbul nyeri. Ini kasus pada inflamatori ya. Adanya prostaglandin tadi bisa disebabkan karena ada sel yang rusak, kita teriris pisau, kulit kita terbakar, sel-sel yang rusak akan mengeluarkan prostaglandin E2, PGE2. dia akan mengaktifkan bradikinin sehingga mengaktifasi neuron nosiceptif. Ada dua enzim yang berbeda, yaitu COX-1 dan COX-2. Kalau COX-1 ini pada kondisi normal, kondisi homeostasis selnya, merubah asam arahidonat menjadi siklik endoperoksida dan terbentuk prostaglandin trombosat. Sedangkan pada kondisi inflamasi, yang berperan adalah COX-2, siklooksigenase 2. Ini yang merubah asam arahidonat menjadi siklik endoperoksida, yaitu prostaglandin E2. Ini terlibat dalam proses inflamatori. Kemudian opiat dapat menghambat reseptor nyeri, neuroreseptor, ya, neurotransmitter reseptornya, sehingga reseptor tersebut tidak akan menangkap neurotransmitternya. Opiat juga bisa menutup gerbang kalsium, sehingga kalsium tidak masuk pada akson terminal, maka neurotransmitternya tidak akan masuk. Jadi dua cara kerja dari opiat seperti itu. Nyerinya akan terhambat. Ini perjalanan nyerinya. Nyeri akan berjalan sepanjang neuron kalau ada influx dari natrium. Pintu natrium terbuka, nyeri ditransmisikan. Nah, natrium terbuka lagi pintunya, nyeri dirambatkan. Seperti itu terus. Apakah ada obat yang menghambat pembukaan pintu natrium? Ada. Kita pernah bicara di dasar, ya, lokal anestetik. Obat-obat anestesi lokal ini akan menutup pintu natrium. Ketika natrium tidak bisa melewati membran, maka sel tersebut, neuron tersebut akan berhenti. Di fisiologi nyerinya akan terhambat, tidak akan disampaikan pada sel-sel yang berikutnya. Jadi nyerinya stop. Ini ilustrasi dari teori gate control. Jadi ada tanda panah yang itu naik ke atas dari dorsal horn naik ke talamus karena ada pintu yang terbuka. Ya, gate controlnya terbuka. Nah, ketika
lecture, we are going to cover the pharmacology of drugs for Parkinson's disease. So let's get right into it. Parkinson's disease is a neurological disorder that results in a progressive loss of coordination and movement. Now, the neurons responsible for coordinating movement are located in a part of the brain called striatum, which receives information from two major sources, the neocortex and a region known as the substantia nigra. The cortex relays sensory information as well as plans for future action, while the substantia nigra sends dopamine that helps to coordinate all of the inputs. Now, Parkinson's disease develops when the neurons connecting the substantia nigra to the striatum progressively degenerate. Since dopaminergic neurons that originate in the substantia nigra normally exert inhibitory effects on GABA neurons located in the striatum, too little dopamine results in more GABA causing increased inhibition of the thalamus, as well as reduced excitatory input to the motor cortex. In addition to that, these same dopaminergic neurons also exert inhibitory effects on the excitatory cholinergic neurons in the striatum. And again, without sufficient levels of dopamine, the production of acetylcholine is increased, which triggers a chain of abnormal signaling leading to impaired mobility. Ultimately, the imbalance between inhibitory and excitatory activities leads to the manifestation of typical clinical symptoms that include resting tremor, rigidity, postural instability, and slowed movement. The pharmacological therapy for Parkinson's disease is aimed at replenishing dopamine levels, mimicking dopamine's action, or antagonizing the excitatory effects of cholinergic neurons. Now, in order to get a better understanding of the pharmacology of anti-Parkinson agents, first we need to take a closer look at the dopamine-producing neuron. So here, inside this dopaminergic neuron, dopamine is synthesized in a two-step process, starting with the amino acid tyrosine. First, with the help of enzyme tyrosine hydroxylase, tyrosine gets converted to L-dopa, also known as levodopa. In the second step, the L-dopa formed by tyrosine hydroxylation is quickly decarboxylated by another enzyme called aromatic L-amino acid decarboxylase to the neurotransmitter dopamine. Dopamine is then loaded into synaptic vesicles and released by physiological stimuli into the extracellular space where it can bind to dopamine receptors that are expressed on the postsynaptic neuron. Finally, excess dopamine in the synapse is reuptaken back into the neuron or into glial cells, where it gets metabolized by monoamine oxidase, abbreviated MAO, and catechol O-methyltransferase, abbreviated COMT. It's important to note that while the MAO enzyme exists in two forms, known as type A and type B, the type that is predominantly found in the glial cells is the MAO type B. Now let's move on to discussing drugs used in treatment of Parkinson's disease, starting with one of the most commonly used drugs, that is levodopa. But first things first, you may wonder, well, why would you use the precursor of dopamine instead of dopamine itself? And the answer is, it's because of the blood-brain barrier. Blood-brain barrier is a tightly packed layer of endothelial cells that restricts free access of molecules between the blood and the brain. Dopamine happens to be one of those molecules that cannot freely pass through this barrier. However, levodopa can, with a little bit of help. One of the biggest problems levodopa faces on its own is peripheral metabolism. There are two major enzymes in periphery which cause breakdown of levodopa before it can reach the brain. That is peripheral dopa decarboxylase, which converts levodopa to dopamine, and catechol O-methyltransferase, which converts levodopa to 3-O-methyl-dopa. Because of this, levodopa must be administered with another agent, called carbidopa, which inhibits dopamine decarboxylase and thus reduces metabolism of levodopa in the periphery. Another agent that is used in combination with levodopa and carbidopa is entacapone, which inhibits peripheral COMT, and thus just like carbidopa, it prolongs the time that levodopa is available to the brain. Now, levodopa is carried across blood-brain barrier by amino acid transporter. Once inside the brain, levodopa is efficiently converted to dopamine, thus supplementing the depleted dopamine levels in the midbrain. However, let's not forget that dopamine is also susceptible to breakdown by COMT as well as MAOB, which convert dopamine to 3-methoxytyramine and 3,4-dihydroxyphenylacetic acid respectively. So here another useful drugs come into play, namely selegiline and rasegiline, which selectively inhibit MAOB, and tolcapone, which inhibits COMT. As a side note here, in comparison to entacapone, tolcapone can better penetrate the blood-brain barrier and thus can act both in the central nervous system and in the periphery. So again, as you can see, by decreasing the metabolism of dopamine, these drugs help to increase dopamine levels in the brain. Unfortunately, because Parkinson's is a progressive disease, with time the number of dopamine-producing neurons decreases, and fewer cells are capable of making dopamine. Taking that into consideration, some drugs have been developed to mimic dopamine and directly stimulate dopamine receptors in the brain. Drugs that belong to this class include bromocriptine, ropinirole, pramipexole, rotigotine, and apomorphine. Now, as I mentioned at the beginning of this lecture, in Parkinson's disease, dopamine depletion leads to increased acetylcholine release, which then activates muscarinic receptors located on the neurons responsible for smooth motor control. The overstimulation of these neurons by acetylcholine then causes tremors and rigidity. This is where antimuscarinic agents come into play by blocking the muscarinic acetylcholine receptors and cholinergic nerve activity. As a result, these anticholinergic agents restore the balance between acetylcholine and dopamine, which may improve the symptoms of Parkinson's disease. Drugs that belong to this class include benztropine, bipyridine, procyclidine, and trihexyphenidyl. Now, before we move on, I wanted to briefly mention here one more drug used in the treatment of Parkinson's disease, that is amantadine. Amantadine doesn't exactly fit into any of the classes that we discussed so far. Its mechanism of action is poorly understood. However, some of the speculated ones are that it prevents dopamine reuptake, facilitates presynaptic dopamine release, and blocks glutamate and MDA receptors. Now, when it comes to side effects, levodopa in combination with carbidopa may cause nausea, loss of appetite, hypotension, mental disturbances, and discoloration of urine, sweat, or saliva. Selegiline and rasagiline may cause nausea, insomnia, dyskinesia, and visual hallucinations. And tacapone may cause discoloration of urine, sweat, or saliva, and diarrhea, which can get severe, particularly with the use of tolcapone. In addition to that, tolcapone has been associated with liver toxicity. All dopamine agonists may cause nausea or dissatisfaction, mental disturbances, and dangerous sleepiness. In addition to that, bromocriptine has been associated with pulmonary and cardiac cirrhosis. Lastly, drugs that block muscarinic receptors generally produce anticholinergic side effects, such as constipation, In this lecture, we're going to cover the pharmacology of anxiolytic and hypnotic drugs, so let's get right into it. The primary use of anxiolytic and hypnotic drugs is to treat anxiety and insomnia. Anxiety is generally defined as an emotional state characterized by excessive feelings of worry, fear, and nervousness, while insomnia is generally defined as the inability to initiate, maintain, or achieve restful sleep. Now, in order to gain better understanding of how anxiolytic and hypnotic drugs work, first we need to discuss the role of GABA in the central nervous system. So, gamma-aminobutyric acid, or GABA for short, is a major inhibitory neurotransmitter. What that means is that when GABA reaches and binds to a specific receptor located on a neuron, it reduces the activity level of that neuron and makes it less likely to fire its action potential. Now, GABA is recognized by both ligand-gated and G-protein-linked GABA receptors. In this lecture, we are going to focus on the ligand-gated GABA receptor called GABA-A, as this is the main target of many anxiolytic and hypnotic agents. Now, the GABA-A receptor is made up of 5 subunit proteins arranged to form a central pore. These subunits have been labeled with Greek letters such as alpha, beta, gamma, and delta. The subunit composition of GABA-A receptors in the brain most frequently consists of 2 alpha subunits, 2 beta subunits, and 1 gamma or delta subunit. Furthermore, for each subunit, many other subtypes exist. The function of each GABA-A receptor depends on which subunit it contains. For example, GABA-A receptors containing alpha-1 subunit appear to be involved in sleep, while those that contain alpha-2 or alpha-3 appear to be involved in anxiety. Now, when 2 GABA molecules bind to the GABA-A receptor, conformational change is induced, which results in opening of the central pore that allows negatively charged chloride ions to rush into the cell. This in turn increases the negative charge inside the postsynaptic cell, which makes it more difficult for an excitatory inputs to cause an action potential. Now, GABA-A receptors are present in high concentration in the limbic system. One part of the limbic system is the amygdala, which contains many neurons that use the neurotransmitter GABA to control feelings of fear and anxiety. In times of stress, excitatory neurons in the amygdala fire rapidly, sending excitatory signals to other areas of the brain. It is this type of firing that leads to feeling of panic or fear. The inhibitory interneurons in the amygdala regulate these emotions by releasing GABA. The release of GABA and its binding to postsynaptic receptors such as GABA-A inhibits the excitatory signals that result in feelings of anxiety and fear. GABA thus has a calming, tranquilizing effect on our emotions and prevents us from becoming overwhelmed in stressful situations. Now, in addition to a distinct binding site for the neurotransmitter GABA, the GABA-A receptor has also a site at which anxiolytic and hypnotic drugs bind. These drugs can be divided into 3 groups, that is, benzodiazepines, barbiturates, and non-benzodiazepine hypnotics. Let's now discuss these one by one in detail, starting with benzodiazepines. So, benzodiazepines get their name from their chemical structure, which includes a benzene ring fused to a diazepine ring. Their binding site appears to be the region between the alpha and gamma subunit on the GABA-A receptor. It's important to remember that benzodiazepines do not bind to the GABA recognition site located at the junction of the alpha and beta subunits. Thereby, they don't induce opening of the channel as directly as GABA. Instead, the binding of a benzodiazepine to its receptor site increases the affinity of GABA for the GABA binding site. This leads to increased frequency of the channel opening and in turn increased influx of chloride ions at the postsynaptic cell, which ultimately makes it difficult for any excitatory inputs to cause an action potential. So when the excitatory signals caused by fear or stress are inhibited in this way, the result is decreased anxiety and greater feeling of calm. In addition to that, benzodiazepines can also produce mild muscle relaxation as a result of their action on GABA receptors in the spinal cord, cerebellum, and brainstem. The examples of benzodiazepines are alprazolam, chlordiazepoxide, clonazepam, diazepam, lorazepam, and temazepam. When it comes to side effects of benzodiazepines, the most common ones are related to their sedating and muscle relaxing action. They include drowsiness, dizziness, decreased alertness and concentration, as well as impairment of motor coordination. Now let's move on to the next group, that is barbiturates. So barbiturates bind to GABA-A receptor at the alpha or beta subunit, which is different from the GABA binding site and also different from the benzodiazepine binding site. Now, just like benzodiazepines, barbiturates enhance the effect of GABA at the GABA-A receptor. However, instead of increasing the ion channel opening frequency, they increase the ion channel opening duration. In other words, unlike benzodiazepines, barbiturates hold the ion channel open continuously for long periods of time. In addition to that, barbiturates can decrease the activity of excitatory neurotransmitters such as acetylcholine and glutamate, and at higher doses, they can also mimic GABA and directly activate GABA receptors, thus leading to profound central nervous system depression. This is why barbiturates have a much lower therapeutic index than benzodiazepines, meaning the toxic dose is not much higher than the therapeutic dose. The examples of barbiturates include pentobarbital, phenobarbital, and secobarbital. When it comes to side effects, barbiturates most often cause dizziness, lightheadedness, sedation, as well as memory and attention impairments. Furthermore, because of their narrow therapeutic index, it's important to remember that even small barbiturate overdose can result in coma or death due to respiratory depression. Now, let's move on to our last group of drugs, that is non-benzodiazepine hypnotics. As I mentioned at the beginning of this lecture, GABA-A receptors in different areas of the central nervous system consist of various combinations of the subunits. The specific subunit that appears to mediate sedation is the alpha-1 isoform. So, as their name suggests, non-benzodiazepine hypnotics are structurally different from the benzodiazepines, and as you may already guess, they selectively bind to the alpha-1 subunit of the GABA-A receptor, thus triggering chloride channel opening with resulting membrane hyperpolarization. Because alpha-1 containing GABA-A receptors are highly expressed in wake-promoting regions of the brain, the preferential binding of non-benzodiazepine hypnotics to these receptors results in sleepiness but not anti-anxiety effect. The examples of non-benzodiazepine hypnotics are zolpidem, zaleplon, and azopiclone. When it comes to side effects, non-benzodiazepine hypnotics can cause cognitive impairments, including memory loss, daytime sedation, as well as impairment of motor function. And with that, I wanted to thank you for watching. I hope you enjoyed this video, and as always, stay tuned for more.